All right. Just for fun, here is the structure of coenzyme A. So now you see why we abbreviate it. It's got a thiol group and a bunch of other things. This is the A part of coenzyme A. You may recognize that as adenine. It's sort of got this long arm that has a thiol on the end of it. The enzyme sort of holds on here, and then this is sort of a handle, a tether that can move whatever's attached to acetyl-CoA wherever it needs to go. So, yeah, understand when we draw it like this is not small. In fact, most of the molecule by weight is actually all of this stuff. Okay, so we've gotten rid of 2 molecules of CO2. There's our second one. We end up with this now 1, 2, 3, 4 carbon unit. It's sort of a dicarboxylic acid, but one of the 2 carboxylic acids is a thioester. Just as a reference point, where we need to get back to now in part 2 of the citric acid cycle is our entry point, oxaloacetate. 1, 2, 3, 4. Comparing those two, the oxaloacetate starting material versus succinyl-CoA, what's different? Well, we lose the thioester, and we need a ketone on carbon 2 instead of just 2 hydrogens, right? Now, getting rid of the thioester, that should be easy. That's thioester hydrolysis. But nature is not wasteful, and thioesters are fairly high energy intermediates, fairly reactive. We can get something out of that thioester, it turns out. And so the next step of the citric acid cycle, step 7, is going to be to exchange that thioester for something that we can get ATP out of. All right, so here's succinyl-CoA. In this 7th step, a molecule of inorganic phosphate. This is just one of the conjugate bases of phosphoric acid, and this is present all over the place in biology. We'll attack the carbonyl carbon, and we're basically going to do nucleophilic acyl substitution. So here's the tetrahedral intermediate. And it actually doesn't matter. We'll just show this conjugate base of phosphoric acid doing things. We won't really worry about the protons on the phosphate group. Here's your tetrahedral intermediate. Electrons kick down, and thiol leaves. Coenzyme A thiol leaves. And the intermediate that we make now looks like this. We went from something that was a thioester bond to something that's a similarly high in energy phosphoanhydride. And we've been here before. We had a similar intermediate that we used for what was called substrate level phosphorylation back in glycolysis. We used 1,3-bisphosphoglycerate basically to do an SN2 reaction where we had ATP attack this ADP attack this phosphorus using the carboxylic acid as a leaving group. We're going to do something very similar here, only the thing that does the attacking is going to be GDP. Why it's G instead of ADP, I don't actually know. And I also don't actually know whether or what the different uses of GDP and GTP are versus ATP and ADP. So don't have a good answer for that. But this is the beta phosphate of GDP. That's going to attack the phosphate of this mixed phosphoanhydride intermediate in an SN2 style step. That's going to release the carboxylic acid called succinate. And it's going to generate GTP as a product. All right, I'm not drawing the structure of GTP because you can look it up, but the point is, well, fine, I want to show the bond that we made, and so you can compare it to the strength of the bond that we broke. Okay, here is the bond that we made, and that installed the gamma phosphate group on GTP. And so that's basically, you can exchange GTP with ATP, so we can count that among the molecules of ATP that we form. All right, so step 7 is all about nature recouping costs and taking advantage of high energy intermediates that we happen to have generated, not letting that thioester go to waste. Okay, yeah?
So it just doesn't do ATP just because you were saying like there's not really a reason. Okay.
There's probably a reason, I don't know it. All right. So we're almost there. Steps 8 through 10 are all now about generating the correct, putting the correct functional groups in the right spot so we can have oxaloacetate instead of succinate. The enzyme that does this reaction is actually unfortunately named for the reverse reaction. Succinyl-CoA synthetase is what you would call an enzyme that starts with succinate and uses GTP and coenzyme A to generate succinyl-CoA. So it's one of those. Why do they do that? Well, because enzymes are catalysts. They don't care about thermodynamics. They don't care about which direction.
Does that other direction ever happen?
Yes. Yeah, does that other direction happen? Yes. I don't know why they... Biology was discovered stepwise here and there. We didn't know how things were, so yeah. Right. Okay, so we need an OH group or a ketone on carbon 2, which is an alpha carbon. Fortunately, we are adjacent to a carbonyl group, so the thing that makes the most sense to do is just sort of enolate type chemistry. That's one thing you can do when you're alpha to a carbonyl group. So let me show you overall what the next step is, and then we'll talk mechanism. Here's succinate, and the enzyme here is called succinate dehydrogenase. And this is aptly named because missing from succinate after this reaction are two hydrogens. Basically, a proton and a hydride are missing. The intermediate shown here with a pi bond between carbons 2 and 3 is called fumarate. You need an oxidizing agent to do this. That oxidizing agent is called FAD. And once it's reduced, it's called FADH2. The mechanism is sort of an E1CB style elimination of a hydride that gets delivered to FAD. So first, a base removes the alpha proton to generate an enolate. Now I'll draw for you the structure of FAD. It's a little bit complicated. I don't really care that you memorize what the structure of FAD is. You should recognize it. Okay. Then this enolate electrons will kick down and hydride gets delivered to the sort of para-nitrogen of FAD. And you push arrows like this to generate FADH2. And I'll draw the reduced form of FADH2 here. This hydrogen and its electrons end up here on FADH2, and then this proton gets picked up from some source, the enzyme or something. So, succinate to fumarate. Fumarate's an alpha-beta unsaturated carbonyl compound. So, getting an oxygen adjacent to one of those carboxylic acids is basically a conjugate addition style reaction. Carbonyl carbon, alpha carbon, beta carbon. OH minus acts as a nucleophile, attacks the beta carbon. That puts the oxygen adjacent to one of the carboxylic acids. I'm showing you stereochemistry there, but I probably didn't need to. The alpha carbon picks up a proton from some source, probably the enzyme. This intermediate is called malate. It's sometimes called L-malate because the stereochemistry is L, whatever that means. Still named using the L and D system. I don't really care that you know what the correct stereochemistry is. This is just a conjugate addition reaction. The enzyme that catalyzes this process is called fumarase. And I don't know. I see the root word for the infinitive form of to smoke in Spanish, fumar, and all of that. I don't know whether fumarate has a smoky aroma or what. Probably not. Probably just a coincidence. All right, and then lastly, remember we need to get to oxaloacetate. That's an alcohol to a ketone. So step 10 is just exactly what you would predict. This enzyme is called malate dehydrogenase, and it involves taking malate and NAD+, and the mechanism here you've already seen in a previous step, right? It's going to be one of these classic deliver the hydride to NAD+ sort of steps. And your final product is NADH and oxaloacetate, and with that, you're ready to go around again. Okay. So it took us all that time to go through that. Meanwhile, your body's been cranking on that like crazy and all the cells in your body so that you can be alive. Okay. Okay, other questions, concerns, comments? The best way to go through that, in addition to sort of brute force memorization, it's going to help you most if you can try to have a sense for the chemical strategy and logic of what's going on here. So remember how we talked through about moving the OH group around so we could have an alpha keto or an alpha beta or a beta keto acid. Having a sense for that kind of logic will help you remember all of the details. Questions on exams that I've written in the past have included, fill in the missing intermediate. So, which is it? Fill in the box. You see a few steps from glycolysis or the citric acid cycle or fatty acid beta oxidation. You have to fill in the right intermediate. For the citric acid cycle or glycolysis, fill in the missing enzyme name. What cofactors help make this process happen. So hopefully that gives you an idea of sort of what to expect. Yeah?
Can you show where the 6 NADH came from, just throughout all 10 steps?
Okay, let's count the NADHs. For one turn of the citric acid cycle, it was 3. Yeah. So let's look. Step 1, no. 2, no. Okay, there's 1. Hold on. There's 2. And then there's 3. Yep. Okay, good. What else? Yeah.
What was the name of the enzyme for steps?
I believe that was, I didn't write it down. You have to go look that up on your own. It's called, actually, you could guess. Isocitrate blank. What do you think it is? Dehydrogenase. Yes, because it's an oxidation reaction. You're dehydrogenating the OH group there to make a ketone. Okay, good. Yeah, isocitrate dehydrogenase. Okay, what else? All right, so now you're going to fly through biochem, or at least the part of biochem that talks about metabolism. And understand we've only talked about the chemistry of one small part of that big, heinous poster I showed you of all the biochemical reactions. All right. So as I told you, my wife is teaching a marriage prep class in the School of Family Life this summer. Today they're talking about sex and eating cake. You guys are having a much funner time, I think, than they are over there. They're eating cake while talking about sex. They're actually eating better than sex cake while talking about sex. It's great, yeah. So I'm sure you all wish you were there. We're going to do chapter 28 now. And chapter 28 is about modern carbon-carbon bond-forming reactions in organic synthesis. And it involves some transition metals and some things that it's going to be a major sort of shift in gear, some things that you're not used to. I want to provide you enough detail so that you can learn more about this if you want to. Some of what I say today and next time is not in the textbook. The reactions are all in the textbook, but some of the stuff about the transition metals is not. To introduce this topic, I want to review some things that we've learned about carbon-carbon bond-forming reactions. So suppose I wanted to make this molecule. What bonds in that molecule do I currently know how to make? You think of a reaction that I could use to get this molecule as a product? Friedel-Crafts, right? And sometimes it's useful to think strategically about the kind of bonds that a given reaction will facilitate. For the Friedel-Crafts reaction, you could use this alkyl halide and this benzene ring. You end up making a bond between these two carbons. That's a bond between an sp2 carbon and an sp3 carbon. So we've got a way to do that, and you know, we would have a similar approach with a slightly different molecule to make a bond between an sp2 carbon and another sp2 carbon, right? Sometimes people will call sp2 carbons attached to benzene rings aryl carbons. So a bond between an aryl carbon and an sp2 hybridized carbon, Friedel-Crafts acylation, we got that. But what about this? What if we wanted to make a bond between two benzene rings? Suppose I wanted to do something like that. A bond between two aryl carbons. Do I have anything for that? Do I have a Friedel-Crafts reaction for that? Problem is, in the Friedel-Crafts reaction, the mechanism involves sort of an SN2 or SN1 style reaction where the benzene ring attacks that carbon in sort of SN2 fashion. And we've never done an SN2 reaction on something like this. You see that, you think, oh great, a leaving group. Can I do an SN2 reaction? There's no SN2 on aryl or vinyl halides. Part of that is because there's a vinyl halide, here's an aryl halide. We've never, ever, ever, ever done nucleophile attacks in SN2 fashion to give me this substitution product, in part because the antibonding orbital for the carbon-chlorine sigma bond is pointed back straight into the middle of the benzene ring, and a nucleophile simply cannot get there because of sterics. Okay? So traditional substitution chemistry doesn't work with the benzene ring aryl carbon being an electrophile. Nevertheless, these biphenyl linkages between benzene rings, or perhaps between an aryl carbon and a vinyl carbon, those are, we don't have really good tools for that, right? Supposing we wanted to make this bond, we can't just do Friedel-Crafts type reactions. So we need another strategy. And there is where transition metals really come into usefulness. So as an example, let me show you a reaction that wouldn't work, or that doesn't work in SN2 fashion, but does work fine for a transition metal complex. So behold the cuprate, that horrible thing that you thought you were done with. The cuprate makes this bond here just fine. But the mechanism is not SN2. It can't be SN2 for reasons that we've talked about. So what is it, and how can we understand it? It's not this. It's more complicated than that. So before we can understand that, we need to know a little bit about the transition metal elements. And I know very little actually about these, but their chemistry is really useful. So I'm going to write down just a section of the periodic table. You don't need to do this. It'll just be useful for our discussion, and so you can look at the screen instead of looking over at the left, my left, your right, to the periodic table. All right, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 groups. Below chromium is molybdenum, below irons, ruthenium and osmium. Below cobalt is RH, rhodium. I don't know why I thought it was RD. And iridium. Below nickel is palladium and platinum. All right. So a couple of things that people talk about transition metal elements. The ones over on the left-hand side are relatively electron poor. These are often called early transition metals. Listed here is the number of valence electrons each one comes with. You're not used to thinking about valence electrons for transition metals, or at least I'm not, because we've stuck mostly with carbon, nitrogen, and oxygen. But that's sort of how you determine how many valence electrons each of these have. The transition metals towards the right-hand side are called late transition metal elements. They are relatively electron rich. You might expect the ones over here to be mostly Lewis acids, the ones over here to be mostly nucleophiles, and the ones in the middle to have the ability to do both. These transition metals form interesting complexes with a lot of different molecules. So we want to talk about how to think about these complexes. So let me give you an example. We're going to come back to this reaction where the cuprate does this coupling reaction with the vinyl bromide. But before we do that, we need to know a little bit about transition metal complexes. So I'm going to show you one. This is palladium, and it's going to be bonded to 4 triphenylphosphine groups. Sometimes that's called tetrakis triphenylphosphine palladium. The PPH3 is a phosphorus bonded to 3 benzene rings like this, so you can see why we've abbreviated that. Now, the rules for drawing transition metal complexes are a little bit different than the rules for drawing organic molecules, because people don't obsess over formal charge on atoms in transition metal complexes. Some of you may have been looking and saying, holy Toledo, Batman, look at those molecules look at all of those bonds that phosphorus is making. 4 bonds to phosphorus. Each of those phosphoruses should have a positive formal charge on it, right? Well, if we were keeping those rules, it's true. Nevertheless, formal charge was only ever about electron counting, keeping track of electrons. And sometimes it didn't tell us very much about where the positive or negative charge in a molecule actually was. If we tried to assign formal charge here, we might end up, this complex overall is neutral. We might end up with something that would say, hey, there's 4 negative charges on the palladium, and we'd have this idea that that palladium was really, really, really reactive and a super strong base, but it's not. So formal charge stops being that useful for transition metal complexes because it stops telling us a whole lot about reactivity. So we're going to drop it completely. Now, we have to show the overall charge on the complex correctly. The fact that I haven't shown a charge tells you that this complex was neutral. If it were not neutral, I would have had to indicate that. Okay? Let me show you another complex involving palladium. This is also neutral. Okay. Now, there are 2 different kinds of groups that can participate in complexes, organometallic transition metal type complexes. The groups that are attached to the transition metal are called ligands. Okay? So, these groups are all ligands. And there are 2 types of ligands. Okay? Number 1 is what we call an L-type ligand, meaning an L-type ligand is neutral when not bonded to the metal center. For example, triphenylphosphine is an L-type ligand. if I take the electrons represented by this phosphorus palladium bond and I take them away with the phosphorus, that the thing that leaves is neutral, right? So here's an example of an L-type ligand leaving a transition metal complex. The complex as it started was neutral. Complex is still neutral, and the thing that left is still neutral. All right. The pattern for L-type ligands is typically lone pairs or pi bonds, pi electrons that coordinate the metal. All right. Coordinate the metal. What does that mean? These electrons donate into an empty orbital on the metal. We're typically not going to worry at this stage about which orbital that is. Okay? So it's easier than you think. You look at the ligand and say, and we say the electrons in the bond between palladium and ligand belong to the ligand. And is the ligand charged or neutral when it leaves with those electrons? So we'll say, yeah, electrons in the ligand metal bond belong to the ligand. Second type of ligand is what we'll call an X-type ligand. I feel like we're talking about Pokemon here. Oh yes, that's an X-type Pokemon. And these are ligands that leave with a negative charge. So an example of that is our transition metal complex here. If bromo left, the whole complex, as I said, is neutral. If bromo left, it would leave as Br minus, which means by definition what's left behind would have to have a positive charge. Notice I'm not bothering to assign where the positive charge is. I'm just saying the overall complex is positively charged. X-type ligands are going to be things like OH minus, Cl minus, Br minus, F minus, I minus. It could also be some kind of carbanion. Like a bond between carbon and the transition metal center. Okay. Now, one thing that's useful in following through reactions involving these transition metal complexes is to understand the oxidation state of the metal, because that can help you tell whether a particular reaction is an oxidation or a reduction. So I'm going to take you through some examples on how to do this. Assigning metal oxidation state. So here's a complex that I think some of you, I don't know, if you took an undergraduate general chemistry laboratory, I'm not sure whether you make this in 107 or not. I think some of the chemistry majors may have done so in like 113. Anyway, this is a complex of cobalt with ammonia. If if I remember right, I think it makes a lovely blue color. Okay, so first, we need to know that the overall charge on this complex is 3+. Somebody would need to tell you that, okay? Then we need to decide what types of ligands we have on that cobalt. We have 6 NH3 ligands, and those are all L-type in the sense that they leave neutral, okay? So then we need to know how many valence electrons does cobalt normally have? And the answer is 9, okay? Cobalt normally has 9 valence electrons. Okay, so we're going to take the overall number of valence electrons from cobalt, 9. We're going to subtract 3 because that's the charge on the complex. So overall, cobalt has 6 valence electrons now. Okay, and we know that the charge on cobalt, the charge on the complex is 3+. We take away all of the ligands, they leave neutral. The charge on cobalt is still 3+. Cobalt normally comes with 9 valence electrons. The only way for it to be 3+ is if it has 6 instead of 9. Sort of follow that through? Not that complicated. Why are we spending time on it? I'll show you in a little bit. So that means that overall, cobalt is at the oxidation state of +3. Now, we said it's got 6 valence electrons. They're all in d orbitals, so we sometimes say that cobalt is a d6 metal, or it has 6 d electrons. Sometimes it's also useful to count the total number of electrons that are participating either on the metal, 6 d electrons, or electrons from the ligands. Total number of electrons here. You've got 6 from cobalt, 6 d electrons from cobalt, and then you have 6 times 2 from each of the ligands, for a total of 18 electrons. And this is a new sort of octet rule for transition metal complexes. The maximum number of electrons that can surround a transition metal is 18, right? You've got, if you look at a row of the periodic table, you got 2 spaces from the 4s orbital, 10 spaces from the 3d orbitals, and then 6 spaces, no? Why am I getting that wrong? 2, and that's right. And then 6 spaces from the 4p orbitals for a total of 18 electrons. All right. So that all seems fairly elementary and unconnected. We are going to get to the transition metal chemistry, and we'll go through some other examples of this. So have a good Wednesday. I will see you Friday. Oh, got the feeling you were a little bit overwhelmed last time as we were talking about the pyruvate dehydrogenase complex. So, thought about it. What questions do you have? It's okay if you don't have any. It's okay if you just want to make the whole thing end. It's going to end very soon, so don't worry. Yes? An overview of just this reaction or like everything? Okay. Yeah, so you're starting with a 3-carbon molecule pyruvate. You've got a carboxylic acid and a ketone. We call this an alpha keto acid. And you need to lose 1 carbon as CO2 to get down to the 2-carbon acetyl-CoA. This is the sort of universal entry point into the citric acid cycle is acetyl-CoA. And that's also the product we get from fatty acid beta oxidation. So all of these molecules are getting shunted to the same pathway. So what we're talking about is basically a bridge between the end product of glycolysis, or pyruvate, and the starting product of the citric acid cycle, which is acetyl-CoA. The other main sort of overview is that alpha keto acids need some help to do decarboxylation, whereas beta keto acids don't. And we talked about that last time. So we're using some cofactors to facilitate this process. And it is an oxidation process. You can tell it's an oxidation because you take NAD plus and go to NADH. NAD plus gets reduced to NADH. And it's an oxidation process over here because in pyruvate, we used to have a carbon-carbon bond between alpha and beta carbons. We now have what used to be our carboxylic acid carbon now has 4 bonds to oxygen instead of 3. And what used to be our ketone carbon now has 3 bonds to a heteroatom instead of 2. So this process has got to oxidize pyruvate and result in losing CO2. All right, I don't know if that's what you were looking for, Ish. What else? Yeah.
I don't remember if we went over this on Wednesday, but where does the NADH come in?
We haven't gotten there yet, actually. Yeah, NADH hasn't. We haven't reduced NAD plus to NADH yet. What we did so far, step 1 was decarboxylation and thioester formation. Step 2 was going from the thioester we have to the thioester we want. We haven't regenerated, or we haven't generated NADH yet. Good, what else? So, just briefly looking at the cofactors that make this process happen, you've got a couple of them. One is this lipoic acid, which has this interesting, weird 5-membered ring disulfide. We're going to use one of those sulfurs to make the thioester. And then thiamine is a catalyst that we're going to use to make it so that this alpha keto acid can lose CO2. And one of the interesting things about thiamine was it has this weird characteristic of being nucleophilic and electrophilic at the same carbon. We talked about how you can draw a resonance structure where you basically have an sp hybridized lone pair on the same carbon as you have an empty p orbital, which is weird. We haven't talked at all about molecules like this, though they're not that rare in organic chemistry, and you can do interesting things with them. But that unique characteristic allows thiamine to act both as a nucleophile and then later on as a place for electrons to go. So we showed the negatively charged carbon of thiamine attacking the ketone. Mechanistically, this step here is exactly the same as we did for making an imine. A nucleophile attacks a ketone. At the same time, the ketone's picking up a proton from another source. And we get a tetrahedral intermediate. But I redrew that tetrahedral intermediate to try to make it clear that thiamine's attack puts this carbon-nitrogen pi bond at the beta position, where it can stabilize a negative charge by resonance. So what you're meant to understand here is this is sort of very much like a beta keto acid, which can now do decarboxylation. If electrons kick down, CO2 leaves behind all of this as a leaving group with a negative charge on what used to be our alpha carbon. So here's the CO2. And we said that this negative charge on what used to be our alpha carbon is now stabilized by resonance, and we can draw a couple of different resonance structures that indicate that it's why this whole thing can be a leaving group is because it's stabilized by resonance, okay? So that's the decarboxylation. And in the next step, again, we're going to see that thiamine is sort of able to stabilize this dual character. It's stabilizing this negative charge by resonance, but in the next step, we're going to see that this intermediate is going to be nucleophilic on the alpha carbon. That makes sense because there's a negative charge there. All right, so in the next step, we have lipoic acid act as an electrophile. The negative charge from the thiamine intermediate attacks the sulfur. The enzyme must control which of the two sulfurs you attack. It's not clear whether one should be more reactive than another, and frankly, from our perspective, it doesn't matter. I'm just showing you what happens. We don't need to explain why we attack one sulfur versus the other. So this is sort of an SN2-like step. We attack a weak sigma bond, form a new carbon sulfur bond, and break a weaker sulfur-sulfur bond. RS minus is the leaving group, which picks up a proton as it leaves. And so then we have this intermediate. I have abbreviated all of the rest of this as SR. You now have a carbon that's attached to an oxygen, a sulfur, a carbon, and another carbon. This is our original thiamine nucleophile, which is going to act as a leaving group. A base removes a proton, electrons kick down, leaving group leaves. That gives us this thioester and regenerates the thiamine ylide pyrophosphate that we started with. And this acetyl group attached to this thioester is the same as this group from pyruvate. All right, so that checks off the thioester formation. Questions you want to ask about that? A lot of arrows. Everybody wants to know, do we need to memorize the structures of these cofactors? Well, it's a multiple choice exam, so I suppose I could say, which of the following is thiamine pyrophosphate ylide, and you could choose the one. Frankly, that would be an easy question. You should all get that question right. Recognizing it is not that big of a deal. Mechanism questions, again, you're not going to be drawing any of this from scratch, but you will need to choose, for example, which mechanistic steps are correct versus incorrect. Yeah. Yes?
So this HPG, is it a good leaving group because that carbon is ready to re-accept the electrons because it's both nucleophilic and electrophilic?
Yeah, why is that a good leaving group is the same reason why we could remove the proton from thiamine to begin with, though. Yeah, it's that the molecule's neutral even though it's got a negative charge on this carbon. Yep. Decent nucleophile, also decent leaving group, which makes it a good catalyst. Yeah.
Sorry, could you point out which one's the trans thioester again?
So that's step 2, which I didn't mention just yet, but step 2 is all about moving this acetyl group from the sulfur of lipoic acid to the sulfur of coenzyme A. We don't necessarily need to draw this mechanism because you could come up with it on your own. It's not that hard. A base would remove a proton to give you the coenzyme A thiolate, and then that would attack the carbonyl carbon. You'd get a tetrahedral intermediate, and you'd kick off the other sulfur. Okay, what else? So the last step, if you notice, you know, in a catalytic process, you want to regenerate, aside from your output, which is acetyl-CoA, you want to regenerate everything so you're ready to begin. And we began with thiamine and lipoic acid. We got thiamine back as a leaving group. The problem is if you compare the structures of lipoic acid here, you've got a disulfide. Versus here, you've got, it's in its thiol form, right? So we need to reoxidize this thiol to the disulfide. And so that's step 3. It's a little bit complicated, so we're not actually going to do the mechanism of that step. I'm just going to sort of show you what happens. So basically you use NAD plus and you get NADH out. And I sort of want to show you where everything ends up. So I'm going to draw the structures of NAD plus. All right, so notice that in your thiol, you have 2 hydrogens, 2 protons that are not present in the disulfide. So you can think of it this way. This hydrogen ends up here. We probably can't tell which, but the 1 proton and then 1 hydride end up on a base and in the NADH respectively. You can imagine, and it isn't actually this way, but you can imagine that a base removes a proton, the sulfur attacks the other sulfur, and then that hydrogen goes to NAD plus. Another cofactor is involved here. It's called FAD, flavin adenine dinucleotide. I'm not going to draw that because you can look it up and we're not doing the mechanism anyway. The part of the complex that does this is called dihydrolipoyl for lipoic acid, and dihydro refers to the fact that you've got 2 hydrogens. And then dehydrogenase tells you that you're removing those 2 hydrogens from your thiol to get your disulfide, and NADH and a base carry away the proton and the hydride respectively. So step 3, you know, by the time we get to step 2 of this 3-step process, we've already got acetyl-CoA. Step 3 is just about regenerating the disulfide so we can go around the cycle again. All right. Don't have to know that mechanism, just want you to be aware of what's happening there. All right. So now we're ready for the famed citric acid cycle, or Krebs cycle, as it's sometimes called. And this is different in that it occurs in the mitochondria, whereas glycolysis occurs in the cytosol. And it's also something that, sorry. I'll show you the overall view of the citric acid cycle. It's got more stuff than you want, but unfortunately, biology and nature in general care very little about what we want and just are the way they are. So here is acetyl-CoA, 2 molecules of that. So I'm writing 2 because in the end we want to total up whatever we've gotten from glucose, and we get 2 molecules of acetyl-CoA per molecule of glucose. So you could simplify this equation a little bit more by just doing 1 acetyl-CoA, but we'll stick with this. 2 molecules of GDP, 2 molecules of inorganic phosphate, and 6 waters because we need to account for protons. Out of this, we're going to get 2 molecules of CO2 plus 6 molecules of NADH plus 2 molecules of FADH2 plus 2 of GTP, and then we'll have some protons that get removed. All right. And we want to point out at this stage that estimates of this vary, but it's around 3 molecules of ATP that you can get per NADH from the electron transport chain, and about 2 molecules of ATP that you can get per FADH2 from the electron transport chain. We're not going to talk about oxidative phosphorylation or proton gradients or anything. We'll leave that to biochemistry, biology classes, but that's the rough exchange rate that you can get. So, you know, if you were to add all of this up, 18 plus 4 plus GTP is sort of an ATP equivalent. We're getting, you know, in the range of 24 to 26 molecules of ATP from the 2 acetyl-CoAs that we take from glucose. Remember that the yield from glycolysis for ATP was what? It's like 2 ATPs plus, I think we had an NADH, so you got to add that yield on there too. But this is like 2 or 3 times as much ATP from this process as we get from glycolysis. Okay, which is why it's great that we have this going on. Okay, this is a 10-step process. Yes? Yes. Say it louder. Sorry. Sorry. What is the number? 2.5 for what? 2.5 for NADH and 1.5 for. Yes, 2.5 versus 1.5. I'm rounding up. So why isn't it exactly 3 or 2, or what is it? What is this approximately stuff? It may depend on cellular conditions. There's also something called proton gradient leakage, where the way that oxidative phosphorylation works is NADH and FADH2 deliver hydride equivalents to an electron transport chain that ultimately reduces oxygen to water. But that process spits protons out the other side of the mitochondrial membrane, driving a difference in concentration inside versus outside the mitochondria. And there are only certain places where protons can come back inside from an area of higher concentration to lower concentration, and as they do, they pass through an ATP synthase. As they pass through that channel, it's like a ratchet. This ATP synthase literally turns and puts a phosphate on the gamma phosphate back on ADP to make ATP. But of course, only passage of protons through that transporter generates ATP. If protons get through some other way, they don't generate ATP, and so that's probably why the process isn't 100% efficient. I'm making that up, I think, based on what I remember from 20 years ago in a biochem textbook. Should I have read it again since then? Probably. Do I care? No. All right, what else? Yeah. So there are different estimates of this. I guess I rounded up. You don't need to know the precise number. All right. So it's good overall. At least what organic chemists bring to the table here is the ability to see sort of what the chemical strategy is. There's logic in all of this. You can see that you're going to get 2 molecules of CO2 out. So overall, what we want to do, our goals are to decarboxylate. And we have 2 potential strategies for that. Strategy A is the easy one. This is decarboxylate a beta keto acid. So this is what we've talked about before, how if you have a beta keto carboxylate group, you automatically have something that can accept the electrons once CO2 leaves. That is, your alpha carbon is adjacent to a ketone such that once CO2 is gone, you're left with some kind of resonance stabilized enolate-like molecule. All right, we've been doing that for a long time. The harder step, the one that requires a little bit of help in terms of cofactors, is decarboxylation of an alpha keto acid. And you've seen this before just barely in that pyruvate dehydrogenase complex. You actually need thiamine pyrophosphate, and you need lipoic acid, and you need NAD+, and that will allow you to, and you also need coenzyme A thiol, and that will give you something like this. Okay, so those are our 2 strategies. We can put R groups in certain places so we're not just stuck with like pyruvate. But those are the 2 strategies you've seen so far for decarboxylating. And those are going to be the strategies we use in the citric acid cycle. So your goal as we go along, we want to manipulate the functional groups to get either a beta keto acid or an alpha keto acid. And then that's it. Everything after that point will be regenerating the starting point, which is a molecule called oxaloacetate. Okay? So much of what we talk about, don't get lost in the details because our goal is arranging functional groups so we can do these 2 things, and then once we've done that, everything else is about getting back to our starting point. All right. So it's called the citric acid cycle because the first step involves formation of citric acid. Right. Okay. So this is the entry point. You take acetyl-CoA, and then the following molecule, which is called oxaloacetate. It is a 4-carbon, 4 diacid with a ketone on carbon 2. So oxaloacetate is itself an alpha keto acid. And the enzyme that does this is called citrate synthase because it synthesizes citrate. Synthase, can't spell. Sometimes enzymes are named in ways that make intuitive sense, other times they are not. This one happens to make intuitive sense. So the product here okay. So let me show you which carbons end up where. Here are the 2 carbons from acetyl-CoA. Those end up here. Here are the 4 carbons of oxaloacetate. Those end up there. Here is the new bond that we made. What kind of reaction do you think that was? Saying something about an enolate, okay. Where did the oxygen from the ketone end up? That OH group, okay. So that looks like something attacked the carbonyl carbon. What was it? It was an enolate, right? So this is really an aldol reaction. It's a 2-part reaction. It's aldol and then it's thioester hydrolysis. Because you'll notice the thioester ends up as a carboxylate group. But yeah, basically we are taking probably some base to generate the enolate from acetyl-CoA. Here's the alpha carbon. That enolate, I'm not going to draw the enolate forming separately. We'll just show removing that proton, making the enolate. Here's the aldol step. Attack the carbonyl carbon of the ketone to get a tetrahedral intermediate, which, if we want, we can show that picking up a proton from some source in the same step. I realize what I'm doing here is condensing multiple things that we've drawn as separate steps in the aldol reaction. Hopefully you can follow it along. Remove the proton to get the enolate. Enolate attacks carbonyl carbon to get tetrahedral intermediate, and now we're protonating the oxygen of the tetrahedral intermediate. So that's the aldol step. Okay, and then this is the step I'm not going to show. This is thioester hydrolysis. All you really need here is water, or OH minus attacks the carbonyl carbon to get tetrahedral intermediate, and then CoA gets kicked off. All right? Questions about that? Now, here's a source of potential frustration. It would be nice if we could follow through these 2 carbons from acetyl-CoA and watch them individually get removed as CO2. And you could do this actually via isotopic labeling experiments if we had particular C13 or C14 acetyl-CoA. Problem is, take a look at the structure of citric acid, or citrate, that we just made. Citrate is not chiral, and this arm here is exactly the same as that arm there. Should we count carbons? 1, 2, 3, 4, or maybe 5 and 6. Basically 3 equals 5 and 4 equals 6. So at this point, we now have completely lost track of our 2 carbons of acetyl-CoA. So you can try to keep track of where they are, but probably it's best just to let it go at this point and just allow, not worry about them anymore, only worry about let's rearrange things so we can get rid of 2 equivalents, two molecules of CO2. One of the conclusions you draw, though, is that it maybe is going to take a couple of cycles through through the citric acid cycle before you've completely gotten rid of these carbons from this particular molecule of acetyl-CoA. All right. Questions you want to ask for Johnward? Okay. Now, remember, our goal is to generate an alpha keto acid or a beta keto acid. Problem with citrate, let's sort of pay attention to where our carboxylic acids are. We've got 3 of them. Right now, we've got an oxygen that's alpha to 1 carboxylic acid, but it's on a tertiary carbon. You can't oxidize that to a ketone, right? In contrast, these other 2 carboxylic acids have alpha carbons here, but their beta carbon is also a tertiary carbon and can't be oxidized. So we're sort of stuck strategically. The oxygen is on the wrong carbon for our purposes, or we can't oxidize it to a ketone. And so step 2 and 3 are going to be about moving where that oxygen is. All right. Let's see. So I'm going to show you steps 2 and 3 together. All right. The first step is an E1CB style dehydration. So a base from the enzyme removes a proton from a carbon that is alpha to a carbonyl group. Okay, and then the electrons kick down and OH minus leaves. And this intermediate is called cis-aconitate. And if you're following through, we just made, we did an aldol reaction, and our product is a beta hydroxycarbonyl compound. Here we've sort of finished up with that aldol reaction doing the E1CB dehydration step to get cis-aconitate, which is an alpha-beta unsaturated carbonyl compound. Okay, so the OH was on the tertiary carbon where we can't oxidize it. We've done an elimination reaction to make an alpha beta unsaturated carbonyl compound. Now let's think try to think strategically. Cis-aconitate is interesting because you have two carboxylic acids, which I'm going to label orange and purple, respectively, right? And they both are conjugated to this double bond. From the perspective of the purple carboxylic acid, this is the alpha carbon and this is the beta carbon. From the perspective of the orange carboxylic acid, this is the alpha carbon and that's the beta carbon. All right? Now, remember that in order to get an alpha or beta keto acid, we need to be able to oxidize this OH group, which we couldn't do on the tertiary carbon. Can you think of a reaction we could do with cis-aconitate that would put an OH group not on the tertiary carbon? Did I hear someone say the magic words conjugate addition? Yeah, what's conjugate addition? Where does a nucleophile attack for conjugate addition? It's 1,4 addition, you attack on the beta carbon, right? If we attacked on the orange beta carbon, that would just be the backward step, right? That would take us right back to citrate. If instead we attack at the purple beta carbon, that is useful because it installs the OH group. So this is a conjugate addition step. Remember, some of the LUMOs on that beta carbon will show the electrons moving on to the alpha carbon. I'll draw the intermediate, but you're going to see that's going to put that OH group on a secondary carbon and is now going to set us up with an alcohol that can be oxidized. So here's the OH group. It's now beta, to the purple carbonyl carbon. Here's the alpha carbon. Right now it's got a negative charge on it. And that's simply going to pick up a proton from some source, the enzyme probably, to give us the product, which is no longer, it's an isomer of citric acid. It's not citric acid itself because the oxygen, the OH group, is in a different spot. Notice that I'm also sort of ignoring stereochemistry, and that's fine. The stereochemistry of all these intermediates is known, but you don't need to know it. Okay, this molecule is called isocitrate. One of the things to pay attention to here, though, is where is that OH group relative to the carbonyls? Relative to the purple carbonyl, that's a beta hydroxy group. Relative to the orange carbonyl, it's an alpha hydroxy group. Guess what we're going to do next? We gotta, before we can decarboxylate, we need that OH group to be what? A ketone. So, makes sense that the next step is going to be oxidation of isocitrate such that that alpha and beta hydroxy group become a ketone. The enzyme that does this step, both of these steps, is called aconitase. Okay. So it's a dehydration followed by conjugate addition. You're literally moving the OH group from this carbon to this one. All right. Questions you want to ask there? Okay, so we're going to do steps 4 and 5 together because one is the oxidation and the other is the decarboxylation. So here's isocitrate. And then I'll draw NAD plus. Oops. And I'll draw it in a particular resonance structure that makes it a little bit clearer where the hydride ends up. Oops. All right, a base, probably from the enzyme, removes that proton. Electrons kick down to make the ketone. Hydride has to leave. It doesn't really leave. It just gets delivered straight to that electrophilic carbon of NADH. Here's the product. Okay, and this product is called oxalosuccinate. Some people draw that in as an intermediate in the citric acid cycle. Others don't because it spontaneously decarboxylates. I'll draw for you the structure of NADH. And we'll remind ourselves that this is payoff. We can take that to the electron transport chain and generate ATP. All right. Now, the beauty of oxalosuccinate is that it is a beta keto acid relative to the purple carbonyl group. All right. So what's going to happen next is decarboxylation of oxalosuccinate. Lone pair electrons on the carboxylic acid kick down, and let me put that off here. These electrons from the bond between alpha carbon and carbonyl carbon end up on the alpha carbon where they are stabilized by resonance. So we just lost CO2. That's one of the two. I'm going to keep drawing the molecule in basically the same shape or orientation, though we may straighten it out a little bit later. Here's the carbon formerly known as purple alpha carbon. I won't draw the resonance structure, but you can see that this is a resonance stabilized enolate. Which can then pick up a proton from some source, probably the enzyme. And we've lost one CO2. What we're left with now is a 5-carbon molecule, 1, 2, 3, 4, 5. And this is called alpha keto glutarate. And it's sort of our halfway point. All right, questions you want to ask about that step? Move the OH group, yeah.
So what causes the CO2 to leave? Is it just a really good and resonance? Or?
It's not about leaving, it's not about CO2 being the leaving group, it's about the fact that all of this is now a decent leaving group because it can leave as something that's neutral, or rather, leave that something that's resonance stabilized. So electrons kick down, all of this leaves, and I didn't show it to you, but the negative charge on this alpha carbon is also on that oxygen, so it's resonance stabilized.
Okay, so it's more stable because the CO2 is neutral.
CO2 left, yeah. So the driving force for this is probably entropy. CO2 is a gas. You breathe it out. I mean, as soon as this happens, it dissolves in your blood and diffuses out, and then you exhale, and it's no longer attached to that other molecule, so there's a large increase in entropy when this reaction happens. Yep. All right, good. What else? Okay, so on our list of things to do, we've done the easy part, which is decarboxylate a beta keto acid. So we can check one of our two molecules of CO2. Sorry, I just looked at my notes and realized nobody caught me on this, but each molecule of acetyl-CoA gets rid of 4 molecules of CO2. This is not Gen Chem. We don't have to balance equations here. Gosh. So yeah, what I'm taking you through is one turn of the citric acid cycle with one molecule of acetyl-CoA. I did this here because I wanted to show you how much ATP we get from the citric acid cycle portion of one glucose molecule metabolism. So for what it's worth, that should be 4 CO2. Anyway, back to where we were. Just looking, we did the aldol reaction, followed by thioester hydrolysis, but we got the OH group sort of in the wrong place for making an alpha or a beta keto acid, so we moved it using dehydration followed by conjugate addition. Then we oxidized the new secondary OH group to a ketone, generating a beta keto acid, which spontaneously decarboxylates to give us alpha keto glutarate. All right, and that's halfway through. Alpha keto glutarate you can actually take and use to synthesize the amino acid glutamic acid, though we won't really talk about that, but you may learn about that at some point. Okay, step 6 is going to be, notice that alpha keto glutarate, this was our orange carbonyl group. This is an alpha keto acid, so it's already set up to do the second, the more difficult decarboxylation step. I won't draw the mechanism of this step because it's exactly the same as what we saw for the pyruvate oxidative decarboxylation complex. There is a multi-enzyme complex, just as with pyruvate, that works with alpha ketoglutarate. It's called the alpha ketoglutarate dehydrogenase complex. As before, it involves TPP, thiamine pyrophosphate, ILID. And it involves lipoic acid, which I'm, again, just abbreviating from above. It's also going to use coenzyme A and NAD+. The product is going to be loss of another equivalent of CO2. And then what's going to be left is this now 4-carbon intermediate, okay, which is called succinyl-CoA, and then also we're going to get NADH. All right, so I won't draw this mechanism in a lot of detail. It's going to involve those same 3 steps that we saw before for pyruvate. So first, TPP is going to attack the ketone to generate a tetrahedral intermediate, which I will draw for you, but just briefly. Okay, that's then set and ready to do the decarboxylation reaction, which puts the negative charge there where it can be stabilized by resonance. Okay, and then those other steps that we saw in pyruvate, this negative charge is then going to attack the sulfur of lipoic acid to generate a thioester. Then you've got trans-thioesterification with coenzyme A, and then you finally have NAD+ regenerate the disulfide of lipoic acid. Okay, so for the mechanism here, just see the mechanism for the pyruvate to acetyl-CoA above, and you've got basically the same thing. Yeah.
Your intermediate's missing carbon.
I'm sorry. Yeah, it is. Thanks. 1, 2, 3, 4. There we go. Sorry about that. Sorry, my first response to everything is as though I were 3. My natural man is a 3-year-old, and he is an enemy to God. And everyone else, so yeah. Got to work on that. Okay, what else? Okay, that may be a good pausing point. Notice that we're sort of halfway there on our list of things to accomplish. We've gotten rid of 2 CO2s. Now I want you to be thinking of how we're going to get from this 4 carbon unit back up to oxaloacetate, which looks basically the same, only it's got a ketone on the alpha carbon. All right, let's take a few minutes and we'll start back up at 9:05.